All right, here we go. What we're doing now, the heat, scorcho, escorcho, okay? I've got nothing better to do than try to explain this in a different way, okay? Another angle. That is the moon. Right? It's my moon. There are no others like it at all. That over there, that magpie, is planet Earth. It's got a diameter of 30 centimeters. There are 30.1 planet Earths in between, let's just call it 30, between the moon and Earth, okay? This is perfectly to scale what we've got here. This is exactly what it would look like, right? If you were looking at both of them from, let's say, I don't know, Venus, right? Earth and the moon. There's 30 Earth diameters in between the moon and Earth, same as there are 108 suns in between Earth and Sun, right? We know that, okay, the average is 384,000, so every now and again the moon will get a little closer and it's an elliptical orbit, but on average this is it, okay? 30 planet Earths in between the two. Now, but we have a bit of fun here, because this is the good bit. It doesn't come around often. So we are to scale, perfectly to scale. How long did it take Neil and that to get to the moon? Let's play along. How long did it take for Neil and Buzz and Michael to get to the moon? About 4 days, 102 hours. So let's call it 4 days to get from there to there, okay? Everything is perfectly to scale. So now, if we had a rocket, a perfectly to scale rocket, taking off of that planet, I mean, we wouldn't see it, would we? Of course we wouldn't. But we would maybe see a tiny plume of smoke going up, right? How long would it take that rocket to reach this moon, all right? Everything is to scale, perfectly to scale. The rocket is perfectly to scale, everything, right? How long would it take for that rocket? How long would we be here for watching that rocket? Would it come and all be over in 20 minutes? Or would it take 4 days? Those of you that said 4 days, who said 4 days, well done. Well done. Those of you that said 20 minutes, if we were on a bus, I'd be throwing you off right now, okay? Because everything is to scale, the rocket is going to take the same amount of time, 4 days. Everything is to scale, right? It's not going to be quicker because it's not the actual distance between the moon and Earth, but it's to scale. So it will remain the same. Now, there's more. That was funny, that moon bit, wasn't it? When I said, how long did it take to go? Right, so what we've got here, how long did it take to get to the moon? Right, now, is that, yeah, okay, I need to make sure I can see. Now, what we have here is another planet Earth, right? And this, I made this 10 minutes ago, chalk, right? 3.6. If I brought that moon over here, put it next to that, it would be the same kind of ratio. So this is there. Everything, it's to scale. It's perfectly to scale. If I took this Earth, there's going to be 1, 2, 3, 4, 30 in between. It's to scale with the size, okay? Perfectly scaled. So, we get to do it again. Neil, Buzz and Michael, July 12th, was it? Is that when they landed? Anyway, 1969. They are just blasting off now from here. Everything's to scale, right? Earth, moon, distance in between, 30 Earth diameters. How long is it going to take for that rocket, if we stayed here and watched it, how long is it going to take to reach that moon? Everything to scale. It would take the same amount of time, 4 days, because everything is to scale. Yeah, mate. Everything is to scale. It will never, ever change, right? it doesn't matter if we make it there and there, tiny, it would still take 4 days, everything to scale, right? So on that, there is obviously never going to come a time, if we get behind this Earth, this is what the moon looks like. It looks roughly like it does when we look at it in the sky. But if I zoomed in more and I got the actual proper zoom, it would look identical. It would look identical from that little tiny one down there from a certain distance. It would always look the same if things are kept to scale. Now, is there ever going to come a time when somebody on planet Earth, it's just down there, see it? There, 30 Earth diameters. So if I go and grab this and go like this, so I've just doubled the distance, right? So now there are 60 planet Earths in between Earth and the moon. But the diameter, the moon's diameter, just bumped up from 3,476 to 7,000, right? Let's say 3, 4, 6, 8, yeah, just about 7,000 kilometers, right? Give or take, not exactly, but for this exercise, it's fine. Planet Earth's diameter just doubled from 12,700, yada yada, to 25,400. So all of a sudden, everything has doubled. But for people on planet Earth, they wouldn't even notice if everything doubled overnight. When they went out and looked at the moon the next day, it would be as it always looks, right? It would always be that same moon, the same distance, the same diameter. It doesn't matter how far. The next day, you'd go to sleep and somebody could multiply it by 1 million. By 1 million, okay? We'd go out, the distance between us would have increased by 1 million, but the moon's diameter would have also increased by 1 million, and Earth's diameter would have also increased by 1 million. We would still see the moon as it is over there now. It would still look the same size, because it will always be in the same proportion as Earth and the distance. There will never come a time where someone would say, hey look, the moon is so far away, it's now taking 1.3 seconds for the light to reach us. That's never going to happen. It can't happen because everything's increasing in the same ratio. And just for good measure, let's do the Earth and Moon and take it to the 150 million that is in between us and the Sun. Average distance between Earth and the Moon is 384,000 kilometers. We've got 150 million. So we divide 150 million. Alexa, what's 150 million divided by 384,000?
150 million divided by 384,000 is 390.625.
So that's how you get what we need to multiply everything by, right? Because we want that distance to become that distance. And to get that distance, we multiply it by 390. Alexa, what's 384,000 multiplied by 390?
384,000 times 390 is 149,760,000.
All right. That's the rounding off thing. We're not going to worry about that, okay? 149, 150 million. If we multiply the moon's diameter by 390, we get 1,355,640. If we multiply our diameter by 390, it equals 4,969, good number, 1,380. So the distance has gone from 384,000 to 150 million. But Earth's diameter has gone from 12,700 to 4,900,000. And the little tiny moon has gone from 3,476 to 1,355,000. So Earth would always see the moon. There would never come a time when you'd expect any kind of delay, because the ratio remains the same. Always. It will always remain the same. So it isn't logical. Look, it's just a no when it comes to 299,700. We've got all of those planets, okay? We're the sun, right? Got this lot, okay? Where we are, actually, well, the sun would be here. Look, something's hit Mercury. It's been bitten by something. We're the sun. This, if sun had a diameter of 27.7 centimeters, right? That's what we would be, right there. Right? That circle is the sun. But you would not see these planets because they would be too small. This is where they would be. But they'd be specks of dust, right? Because they're so small. We've got a small sun compared to what it really looks like. But this is the scale it would be. So if you were living on Pluto and you could use your eyes, right, you might be smaller, but you would still be able to see the sun when it was turned on up here. The scale, this is to scale, right? This is to scale. Apart from Earth missing, but we've got him over there. He gets paid twice, don't worry. There is never going to come a time when we're too far away from the sun to not see it instantly, right? There is never going to come a time when the light from the sun is not absolute. Let's scale. Without the numbers, and it's all their numbers. If we didn't have numbers, all we had were diameters of things, right? Which is obviously the better way of measuring everything, because you do not fuck up. A diameter is a diameter. There would never come a time when that monster up there is too far to give us anything other than absolute light, because that is the only light there is. There is no travel time. It's illogical, and somebody needs to seriously prove it. Look at it. Anyway, that's it. If you still don't get this, right, why it takes 8 minutes and 20 seconds, then I made a mistake. That sun, I just realized that 27.7 centimeter sun was for us when we were planet Earth down by Pluto. So ignore that last bit. 8 millimeters. We are a sun right here, and our diameter is 8 millimeters, right? It's going to take 3 minutes to get there, another 3 and a bit to get to here, and then another 2 something to get to planet Earth. Literally, we would be watching the light going like this. 8 millimeters, 4.6 seconds each diameter, right? And there are 180 of them between here, 100 8 millimeter diameters between here and there. Between here and... It's impossible. It's illogical. It's common sense. It's not rocket science. And that reminds me, where's that rocket? Because it's got to do thrust in a vacuum, so we're not going to be too sure about where it's gone. It might not have been able to turn around. We don't know, do we? We never have seen one turn around in a vacuum, have we? Just saying. All right, that's it. Want some cheese, mate? Cheese? Want some cheese? Huh? Cheese? Right, later, peeps.